Hello, my name is Marshall Clifton. I'm going to be presenting some work I've done with Charles Gretton on parallelizing property-directed reachability. Property-directed reachability, PDR, is a sound and complete planning procedure which maintains and iteratively tightens reachability information about the system. This reachability information, known as layer information, is at the core of PDR. This is a compact formula which is tightened by finding no goods in the system. PDR involves iteratively considering states and trying to progress them one step towards the goal. If it can, then an attempt is made to progress a successor state, another step towards the goal, and so on. If no successor state exists, then the original state is generalized to form a no-good, which is used to constrain the reachability information. This is done using SAT planning techniques and involves calling a SAT solver on a lot of small subproblems. A bit more specifically, let me introduce the notion of an obligation. This is a state combined with an estimate of the number of steps away from the goal it is. PDR then maintains a queue of obligations to process. PDR also maintains, for each number of steps away from the goal, I, a formula which represents an over-approximation of all the states that can reach the goal in I steps. Initially, this is the loosest possible over-approximation, assuming everything can reach the goal in I steps. PDR then processes the obligations in its queue and finds no goods to constrain this over-approximation. If no plan exists, it is possible to constrain this reachability information to a point where PDR can show that the initial state cannot reach the goal, and this is how PDR proves no plan exists. So this is a diagram of serial PDR. The blue rectangle is a single PDR process with a queue of obligations, one obligation being processed at a time, and a collection of layer no-goods. There are existing parallelizations of PDR which have a portfolio of PDR processes sharing no-goods between themselves via a central repository, which accelerates PDR. We take this one step further, introducing a central global queue of obligations. Each process then evaluates obligations from this queue. We find this works better in practice, as each process is working on a similar part of the problem, and the no-goods found by each of the processes are more relevant to each other. We call this method parallel state PDR. The existing parallelisms have a portfolio of PDR processes with various schedules for sharing no-goods between them. There is a technique known as obligation rescheduling. I won't go into detail on how it works here, but is important for efficiency, and the existing implementations do not use it. The existing implementations are also exclusively for hardware and software model checking problems. Because of this, we re-implemented the portfolio approach for baselining against our new approaches we wanted to test. This was especially useful because we could use the same data structures, SAT solvers, and general implementation between approaches, so our comparisons are based on algorithm differences as opposed to implementation details. We also present a method we call parallel decompositional PDR. I won't explain this technique in great detail, but I'll give a high-level overview and a worked example. This technique involves projecting the original problem onto a collection of subproblems, each representing some element of the original problem. We then solve each of these subproblems independently in parallel. To find these subproblems, we first construct a dependency graph, then find its strongly connected components. For example, here on the right, we have a simple logistics problem. The dependency graph is shown with the solid lines, and the SECs and the relationships between them are shown with dotted lines. We can see we have an SEC for each package and the truck. Similar to some planning in abstraction methods, we then take these SECs and create a total order from the partial order found in the graph. Here we have that the two package SECs come first, followed by the truck SEC. Then, for each SEC, we create a corresponding subproblem, each having the same initial state, action set, and goal condition as the original problem, but projected onto only the components which are relevant for that SEC. Additionally, we add a constraint to the goal condition, which, loosely speaking, enforces that any resources used when solving for the goals relevant to the SCC, are returned to their original starting position. So, for instance, when creating a subproblem for a specific package, only the package itself and the transports able to affect that package are included in the subproblem. Additionally, if the truck is moved, then the goal condition enforces that it needs to be returned to its starting position. We then solve each of these subproblems, and if plans can be found for all components, they are concatenated to form a concrete plan. This concrete plan is then checked for validity. As each of these subproblems are planning problems in their own right, they can all be solved independently in parallel. Because we are imposing additional constraints, this is a sound but not complete procedure. We, however, find it works quite well in practice. There was only one instance we found in our testing where this method failed due to its incompleteness. As an example, consider the previously mentioned logistics problem. In our initial state on the left, we have two locations with two packages and a truck at location 1. Our goal condition is that the truck and package 1 are at location 2. If we were planning for this normally, we would put package 1 in the truck, drive the truck to location 2, then unload the truck. With parallel decompositional PDR, we first plan for package 1, achieving only the goals which are relevant to it, which is just moving package 1 to location 2. We drop all mentions of package 2 as that is independent of package 1, and also enforce that the truck is moved back to its original position in the goal condition. So here we load the package into the truck, drive the truck to location 2, unload the package, then drive the truck back to its starting point. We don't need to worry about package 2 as it is not mentioned in the goal condition. We then plan for the truck, which just involves moving it from location 1 to location 2. We tested all the methods described here on a series of benchmark problems. We compare parallel decompositional PDR with parallel state PDR, which is the parallel method with the centralized queue, as well as our re-implementation of portfolio PDR. We also include a standard serial PDR process. These 4 methods were implemented by us and use the same general setup, data structures, sat solver, and so on, so that the comparison between them is between algorithms, not implementations. As an external baseline, we also include timing data for PDR Plan, a serial PDR implementation created by Martin Suter. Each solver was run on problems from a series of domains, each with a 30-minute timeout. Parallel decompositional PDR used 1 core for each subproblem, and the other 2 parallel processes each used 48 cores per run. The distribution of these runtimes over the problems in each domain are shown as bar graphs here. From the left, the domains are logistics, rovers, satellites, TPP, and xenotravel. We see here that in the satellites domain, all solvers time out on some problems, and in xenotravel, parallel state PDR seems to perform the best overall. We also have some results for domains that were not susceptible to the decomposition used in parallel decompositional PDR. These are the optical telegraph domain, dining philosophers, pipe sold no tankage, pipe sold with tankage, and the storage domain. We see that overall, our parallel PDR methods perform better than our serial baseline, and parallel state PDR performs better than the PDR portfolio. Thank you.